Hello, I'm Canchen, and today we'll be going over generic data types. In this lecture, we'll go over, as mentioned, generic data types, and we'll also cover smart pointers in Rust. So, as our motivating example, we've seen in Rust that several types can contain other types. So this is most often featured in collections, where we have vectors can contain a bunch of other, like something of a different type. The same with arrays. Hash maps can contain an arbitrary key and value type, right? And then we're familiar with how option contains sum and then a type, and then result contains both a type for the OK and then a different type for the error. And the question is, how do they do this? How are they able to abstract this to work with many different types? A different motivating example is if we consider these two functions on the right, where largest I32 finds the largest element in a slice of I32s, and largest character finds the largest character in a slice of characters, we see that both functions basically do the same thing, but they just have different function signatures. And if we wanted to maybe like copy this function but for a different type, like U16s, we have to rewrite the same code again, right? Is there any way we can reduce the boilerplate? Hint, hint. So this is where generics come in, where generics are used as stand-ins for other concrete types. And this works similarly to templates in C++. We can use generics in the definitions of structs, as in vector t, enums, like option or result, methods, and functions. And we'll look at all four of these in the upcoming slides. So first, let's cover generics and structs. So here we have a struct point t, which means a struct containing members with generic type t. And then here we see that x and y can be any type. That's what t stands for. But they must be the same type because they are both of type t, right? But what if we wanted them to be of two different types? Well, on the next slide, we see we can just define it to be with two different types, right? And then the rule is if we must explicitly list all the different generic types of the members in the struct definition up here if we want to use them down here. So maybe looking at the code, we see here point t, both x and y have to be of the same type, and so we can't assign them an int and a float. But here, since we defined it so that t and u are different types, we can specify that t is an integer while u is a float, and this code will work. Now we can look at generics and enums. So if we'll recall back to when we discussed about enums, we know that sometimes enums can have variants that contain data. So in this case, we define enum for a number where if it's finite, it contains that number, or if it's infinite, it's a different case, right? And we can use it as you would expect, but the key thing to note here is that even if we are using a variant of the enum that doesn't contain the type t, we still need to declare the concrete type. So here, even though this infinite variant of the number enum does not contain any data, we still need to specify that this is a number U32, such that if this were finite, it would contain a U32. Also, here's a different example, right, where we have generic types t, u, and v. And even though none of the variants use all the different types, when we declare the type definition, we still need to specify all three different types, even if they aren't being used. And then here are some examples of where you've probably already seen generics in enums, right? Remember that option t is defined technically like this, where the sum variant contains any arbitrary type, and that result has an OK and error variant, where the OK variant takes a value of any type, and the error has a different value of an error type, right? Now we'll cover generics and methods. And the way we can do this is we can use impl t point t. And this means that the methods in this implementation will work on points with the generic type t. So this code basically says for any point, we can have it return its x value, even though it's a generic value and we don't know what that type might be. But why do we need to make this distinction that we are specifically implementing it for this arbitrary type t? And that is because we can specify a concrete type that we want to implement it for as well. So here, we can implement something specifically for points of I32, this distance from origin function. And this will only apply to points of the type I32. So here in this first case, this code works. But when we have a point with floats, and we try and access this function, we'll see it's undefined because it's only defined for points with I32, right? The final examples of generics are generics and functions. If we go back to our motivating example of these two different functions that are designed to find the largest value, we can combine them together with this generic type, right? And this helps us reduce the amount of boilerplate code we need to write, since we can use basically the same function for these two different types. But actually, this code will secretly not compile, and there's an error here. And the reason this happens is this comparison isn't defined for all types, right? For example, what if our type happened to be a hash map? How do we compare that, right? We will go over how to fix this problem in the next lecture where we cover traits. But for the time being, we'll just leave this as like an unsolved problem. Although Rust provides some helpful suggestions as to how we can fix it. Now we'll move on to the section where we cover smart pointers. So you've probably worked with pointers in C++ before. We call these raw pointers. And they basically, all they do is contain an address in memory. In contrast, smart pointers function similarly to raw pointers, but they have additional capabilities. So for example, we're probably familiar with how string and vect technically like point to some data stored on the heap, but in this case, both string and the vector own that data, and they also know some extra metadata about that data, like for example, the length of the string or the length of the vector, right? In Rust, these smart pointers also take ownership of the data that they point to. And then when the smart pointer goes out of scope, the data it owns is also dropped on the heap. So this eliminates the need for you to manually use like new and delete in C to manage memory. It is automatically managed by these smart pointers. And again, because of these ownership rules, safe Rust doesn't let you use raw pointers. But if you use an unsafe block, you can technically use raw pointers, but it's generally discouraged. And then again, most pointers in Rust are smart pointers. We want to use smart pointers since they are safer. And the core smart pointer that we will introduce is the box, right? So unlike the vectors or strings, the data that's stored inside the box doesn't need to be a collection. It lets you store any arbitrary type of data on the heap. How the box works under the hood is that the raw pointer is on the stack. So the physical like pointer is on the stack that holds the address of where the data is in the heap. And then when this pointer on the stack goes out of scope, box will automatically free the data on the heap. So you don't have to manage it manually with new and delete. How we can use it is pretty simple. We just call box new, and then we specify the data we want the box to hold. We can make the box mutable if we want to modify the stored data. And then to get the data out of the box, we can use the dereference operator, just like how pointers work in C++. And this might sound a little familiar to something else that we've covered, right? References, where they both work kind of like pointers, and they both have the functionality that they ensure that the data they point to is not null, right? But the core difference is that box owns the data it points to, and then when the box goes out of scope, the data also gets freed from the heap. But in contrast, references only borrow the data they point to, and the data is owned by some other variable. In both cases, if you wanted a nullable pointer anyways, you can always wrap it inside an option, right? Where you're forced to check if it's null or not. So these are some reasons why box is safer than raw pointers. And maybe some questions you might have are, why should we use boxes? And we use them when we have a type whose size can't be known at compile time, but we want to use that type in a context requiring an exact size. So this is anything involving the stack. Conceptually, the size of the stack pointer will be treated as said exact size. So if we want to put something on the stack, we need to know exactly how much memory to give it ahead of time, right? But for example, if we need something like a resizable array, we don't know how many elements will be in there ahead of time. So that's why the physical data is stored on the heap, but the reference, the pointer to it is stored on the stack. So boxes are another implementation of that. An example would be if we tried to implement a linked list, which we'll see up here. Suppose we describe each node in the linked list to look something like this, where we have it stores some data, and then it stores a pointer to the next link, right? In this case, this code will not work. We'll start off with this wrong implementation. And why is this the case? Well, we see that we don't know the exact size of link, and link lives on the stack by default. We don't know because this link could potentially contain another link, which could contain another link, which could contain another link. So this could potentially have like infinite size, and we don't know. But if we try and compile it, Rust will offer a helpful suggestion. Maybe we should wrap it in a box so that we can put the physical link data on to the heap. And the correct implementation would be to wrap the pointer to the next link would be to put the next link on the heap and then keep the pointer on the stack using the box. Since we know that the pointers have a fixed size, this gets around the issue of potentially having a struct of like infinite size, right? That covers all the content for this lecture. As some reminders, Homework 8 has been released today and it'll be due in a week, next Thursday. And then MP2 was released yesterday and it will be due 2 Wednesdays from now. Thanks for listening.